Alright, welcome back. So today we're going to look at some of these ideas of regression. Right? Regression, these methods apply when we're looking at bivariate data. Right? So what does bivariate data mean? Two variables, right? Because a lot of the methods we've been looking at are, okay, what's going on with one variable? Maybe can I compare two groups with regards to a single variable, right? But the world isn't that simple, right? Most studies we're looking at are going to have a whole bunch of variables, right? And maybe we want to see, we've got a data set with a bunch of variables, and we want to see, are there any sort of relationships here? All right, so each individual, so we'll just keep it to two for now, bivariate, right? But you can go multiple with this. All right, so let's say we have readings or we have measurements of a single individual from two different variables, right? And the kind of questions that we want to answer are, is there some sort of relationship here? Is there some sort of what we would call an association, right? If I change one, does the other change? Does one maybe explain the other? Okay, so the wording usually used here between those two variables, and usually we call our y variable our response, and our x variable our explanatory variable. Okay, so the terminology varies depending on the source, right? You may have been exposed to this idea of your independent versus your dependent variable. The independent variable is one I'm changing. The dependent variable, I'm seeing what sort of response is there. Right? Sometimes your x, your independent or your explanatory variable is also called your predictor. Because ultimately what we're trying to do is we're trying to use values of this x variable to predict what's happening in y. All right, this relationship that we're looking for, this relationship that we're talking about, the word that we like to use is there's some sort of association. All right, so some pretty simple examples, you could probably come up with some off the top of your head, two variables that you think would associate together, right? Like where you sit at a game has some sort of association with the price of that ticket, right? The better seats, usually the more expensive the price. Or sometimes we have a relationship like this. Now we would have a pretty good understanding that your stress level and lack of sleep, right, are somehow related. But sometimes, so I think we see definitely a relationship here, right? The better your seat is, the more expensive your price of your ticket's going to be, right? But sometimes we may have an association where we're not really sure, okay, what's causing what, right? Yeah, the more stressed I am, it might cause you to lose sleep, but also the lack of sleep might cause you to be stressed, okay? So sometimes it's kind of like a chicken and egg type situation, right? Which one came first? All right, both of these examples are numerical or quantitative versus quantitative, right? Something like this, the age and your distance of commute. Right? These are two quantitative or two numerical variables. There are regression methods for looking at other types of data, a categorical versus a categorical, or even a numerical versus a categorical variable. Now we're going to focus on this first type of relationship here, quantitative versus quantitative. So let's look at these with a problem here. And if you're younger and you're listening to this, maybe a lot of younger people tend to not really be into baseball as much. All right, so baseball, Major League Baseball was trying to figure out, well, why is that? And what can we do here with our game? Well, one of the big things that people say about baseball is the games are just too long. All right, so it looks like we got some numbers here. 1981 is about 2.5 hours. And then when baseball started trying to first recognize their issues, the average game had jumped to 3 hours, and now it's actually even longer. All right, so they commissioned a study here, and the main thing they were focusing on was trying to decrease the entire time of game. All right, so they did a whole big study. They collected a whole bunch of data. Here's kind of a cross-section of the data that we're going to work with. All right, and you can kind of see some of the variables that we might work with here. So maybe you could look at these variables and think, okay, there should be some relationships here. All right, now maybe the first obvious relationship would be, well, if a game goes into extra innings, well, yeah, it's going to be longer. Okay, but that's a binary variable. It's a 0 or 1. Probably wouldn't be that interesting. Right? Maybe more interesting might be, what about some of these other variables, like runs, hits, pitchers used? Maybe some of these variables would affect time of game. Okay, so we've got some ideas in our mind, but how do we actually quantify this? How do we actually look at this? Well, we've got two quantitative variables, and like with anything, we always want to take a look at things visually first. All right, so we'll start with the graph. All right, that's what we're going to look at first. Then we'll look at our graph and we'll try to talk about what we're seeing, identify some patterns here. All right, then once we know what we've got going on visually, we'll try to describe this relationship numerically, and then we'll try to model that relationship. Modeling that relationship, that's what regression is. Okay, so let's start with at this graphing point. The graph that we're going to use to look at two quantitative variables is a scatter plot. Right, you've probably seen a scatter plot before, right? Usually we put our dependent or response variable on the y-axis, our independent, our explanatory variable on the x-axis. Right? Then we see where do those readings from each individual intersect and put a little dot. Right? Then we get a collection of dots and we look to see what kind of pattern we have going on. Okay, so here's some scatter plots of some of those potential explanatory variables with time of game as the response. Okay, so here's pitchers as my x, or as my predictor, with time of game as the response. Here's runs scored. Here's hits. So the question is, out of these three, pitchers, runs, and hits, what's the best predictor? Okay, I've got best in quotes there because what does that really mean? What does best mean? And maybe you can look at these scatter plots and you could think, well, it looks like the most obvious pattern is probably here, maybe the tightest pattern. Okay, so maybe you would say pitchers, but runs scored, there's probably something, looks like there's some kind of pattern going on here. Hits, looks like there's a pattern there too. All right, so maybe it's not so obvious. All right, so we start with the graph. So what exactly are we looking for in that graph? Let's look for that pattern. All right, then we'll get to numerical descriptors and modeling. All right, when we're looking at a scatter plot, there's three main things we're looking for: the shape, the trend, and the strength. All right, here's some of the shapes we might be looking for. Here's how we'll describe the trend. And the strength is how tight is that spread. All right, we'll also look for, now we're used to looking for outliers in graphs, and we'll in a sense look for outliers, but it's a little bit different in the bivariate case. Okay, so we'll talk about that a little bit later. All right, shape-wise, we know what a linear shape would mean, right? That's a straight line. If I could draw sort of a straight line through these points. A nonlinear shape is everything else, right? Where, maybe there's an exponential shape like this or some sort of curve shape like this, okay? A linear shape, we can see that straight line. A nonlinear shape, there's definitely something going on there, right? But nonlinear shapes take much more complicated and involved methods. Okay, so for now we're focusing on linear. Nonlinear, okay, that's interesting. Maybe we make a note of it, but then we're not really talking about those methods right now. Right? Sometimes, just as interesting as finding a shape, if I go into something expecting a relationship, but I could potentially find no relationship. Now, I think it's pretty obvious why this graph shows no relationship, right? It's just kind of scattershot. Everything's all over the place. Right? But what about this? Sometimes people say, well, it looks like we could draw a straight line through these points. Why is there no relationship there? Well, think about what this means. Okay, we've got x here, we've got y here. What a relationship like this means is as x is getting bigger, y doesn't really seem to be changing. Okay, so that's why we would say this is no relationship as well. All right, let's look at an example here. We've got, so I graphed the data on people's age and the time it took them to finish a marathon. Right? This may be a situation where you think there would be some sort of relationship. So think about what you think that relationship might be. Now let's actually look at the graph. Right? We see that there actually does not look to be any sort of relationship here between age. There does look to be maybe an optimal age. It looks like actually people around 40 are running the fastest marathons. Right? But we've got young people running fast. We've got old people running fast. Okay, so this example is meant to show, right, that if we go into something thinking there will be a relationship, sometimes it can be just as interesting to find no relationship. All right, the big thing about shape, we always want to look at it first because what the methods that we're looking at only deal with linear patterns. All right, there's other methods that I mentioned, but right now we're just dealing with linear. Okay, so what are we in? So that's shape. Now what are we interested in with trend? A trend, once we've identified linear, right, typically we're looking for a positive or negative trend. So let's see what those look like. So a negative trend has sort of this downhill direction, right? With as x gets bigger, y tends to get smaller. A positive trend has this uphill direction. As x gets bigger, y gets bigger. Sometimes a negative relationship, it might be called like an inverse relationship. Right? Positive, we could say, varies together. So we know about shape, we know about trend. What about strength? Strength of association tells us our spread is pretty large. Yes, there's an apparent pattern, but all of our points don't fit that pattern very tightly or very nicely. A strong association means they fit our pattern pretty tight. Right? So a perfect, very, very strong relationship would be where our points kind of like connect the dots, right? All of our points line up perfectly. So these are both positive linear trends. This one is stronger than the other. This one's still pretty obvious, still pretty strong, but not as strong as a perfect one. Summing up what I'm looking for when I'm describing this association, right, we want to talk about shape, we want to talk about trend, we want to talk about strength. And again, we'll talk about in the future, what if we see kind of weird observations. All right, so back to our example. Keeping all of that in mind, what do we think is the best predictor? And that would probably be pictures, right? These all have positive linear trends, but pictures seems to be the strongest. So simply interpreting the scatter plot of pictures, right, the shape is linear, the trend positive, the strength pretty strong. So I think shape's easy, trend's easy, especially when we're working with linear stuff. Strength is where things get a little bit sketchy, right? Looks pretty strong is how I described this one, right? But that's not very specific. That's not very precise, right? And what we'll find when we're trying to figure out strength, our eyes aren't always the best way to go about this. So check out these two scatter plots here. The one on the left, the one on the right, they both exhibit positive linear trends, right? But which one would we say is stronger? So just at first glance, right, you would say, yeah, this one's much, much stronger, the one on the right. All right, but look closer. Both of these graphs actually show the same data. We just played around. We kind of zoomed in on the one on the left, zoomed out on the one on the right, played around with the axes. Okay, so zooming in, zooming out. Scatter plots are very easy to kind of misinterpret or maybe play tricks on us. All right, I want to show you another example of that. So here's an example of metabolic rate. 19 people, their resting metabolic rate, their body mass, and their gender. All right, so say we wanted to see some associations here. Now maybe we would think there's an association between your weight and your resting calories burned. So let's look at a scatter plot there. So using someone's weight to predict their resting calories. All right, so we see again positive linear trend. But I think we can see something else going on here, right? I think that the trend is pretty strong down here, right? But as we start going up, things seem to be more spread out. All right, so there's definitely a positive linear trend, but something else at play there. Okay, our trend is getting weaker as mass goes up. So what's going on there? Well, remember another variable that we have, right? We looked at these two versus each other. But remember another variable we have, a categorical variable. Maybe there's an association between gender, right? We know that in general, men are probably going to be heavier than women, right? So maybe there's something going on there. There's two ways that I could examine this. I could have the men on one scatter plot, the women on another. But we've seen comparing two scatter plots side by side can be sort of misleading from time to time. If I'm trying to compare two groups, probably what I want to do here is have it all on one plot, right? But plot the females and males differently. Okay, so let's look at this scatter plot again with this positive linear trend. Now we see, okay, look at the blue dots, those are females, and look at the males, the red squares. We see almost different trends for either one. They're both positive and linear, but the females are much tighter, right? They're much stronger. In general, so the conclusions we could draw from this, in general, females weigh a little bit less, but they follow this trend a little bit better than males. Males weigh more. The trend isn't as pronounced for males. Of course, we don't have as many males in this study either. All right, so all of that to show kind of the basics of what we're looking for between relationships in groups. All right, we start with the graph. We look for a pattern. So now is where we come to actually putting some numbers to this thing. We'll start with just basic numerical descriptors, then we'll move into modeling. That's actually what we call regression. All right, the numerical descriptor that we put on these relationships, right, we know how to look for it in a scatter plot, and we know how to describe it, right, but let's put a number on it. That number is called our correlation, or in general, our correlation coefficient. We denote that as R. Right, this specific measure here is called Pearson's correlation coefficient. All right, so here's how it's calculated. A lot going on there in the formula. Most of the time, we'll just leave that up to software. Right? We don't want to mess around with that formula too much. All right, so let's see how correlation works. So there's how it's calculated. So how does it work? All right, here's one scatter plot. Positive, linear, strong, very strong relationship. All right, if I were to do the math, this scatter plot has a correlation of about 0.9. Let's look at another one. Positive, linear, not as strong as the one to its left. This correlation, probably about 0.5. Let's look at another one. Let's compare, so we just compared these two. Right, now let's compare these two. All right, this one's positive linear, this one's negative linear, but I would say that these two have about the same strength. The R value for this one, negative 0.9. All right, so maybe you're catching on to a pattern here of how R works. Top right, negative, not as strong, negative 0.5. Something like this, no apparent pattern, that's R of 0. Something like this, there is a pattern, but it's not linear. All right, Pearson's correlation coefficient only works for linear data. We would give that an R of 0. Okay, so hopefully from this you can kind of tell how R works. All right, so R is always going to be a number between -1 and 1. Positive 1 means a perfect positive correlation. 0 means nothing going on there, or no linear. And -1 means a perfect negative correlation. All right. So the further away that I get from 0 with R, the stronger the correlation is, the further I get to those endpoints. Right, so R actually does not come along with any units, right? And outliers actually would affect it. Okay, so remember in our baseball example, we've got pitchers here. We said it was pretty strong, pretty linear. All right, turns out our correlation coefficient, that's pretty high. That's 0.8. All right, our correlation coefficient with runs in time of game, still positive, but not great, 0.37. All right, hits in time of game, almost 0.5. So where a correlation coefficient is really useful is judging scatterplots, right? We've talked about how it's kind of hard, it's kind of tricky sometimes to judge these things visually. Now when I have something obvious, like pitchers is obviously the best, right? So that's pretty obvious. But what if I'm comparing these two? What's better? I would argue that it's not so obvious visually which one's better. But comparing numerically, now it's obvious that hits is a better predictor of game time. All right, one more numerical measure of relationship here. That's R squared. R squared is our coefficient of determination. And I simply calculate it by taking R and squaring it. R squared, easy enough. Okay, so what does R squared actually mean? Well, we could think about it as the proportion, or often the percentage, of the variability in y that can be explained by x. All right, so like I mentioned, usually we express it as a percentage. So what that's telling us is that a larger value of r, therefore a larger value of r squared, is going to tell us how spread out things are. Right, and again, it tells us what percentage of y can be explained by x. All right, so for our example, the calculation's really easy. For our example, pitchers, that 0.779 squared gives us 0.6, or about 60%. All right, so we're moving down this list. We know about graphs. We know what to look for in those graphs. Now we know how to describe them numerically. So now let's look at this mathematical model. All right, so to model, again, everything we're working with here is linear. Okay, so this thing called our regression line, that line that we kept drawing through those points that we thought kind of connected those dots closely, right, now we're going to define that line mathematically. All right. So the type of regression that we're using here is called least squares regression. And here is the formula for our line. It's just a simple straight line, right? Y equals our y-intercept, and B1 here is our slope. Now one way to calculate that slope, take R, multiply it by the ratio of the standard deviations of x and y. B naught there is our y-intercept. Usually the way that's calculated is once I find my slope, solve for the y-intercept using the mean of x and the mean of y. All right, now these are ways of, so once I find B1, I do that, mean of x, mean of y. These are ways of calculating beta B naught and B1, but again, kind of like R, because there's a lot that goes into calculating that. Usually we just want to leave that up to a computer. Okay, so let's go back to our example using pitchers to estimate time of game. Turns out its regression equation looks like this. All right, so how do I interpret that? Well, our line looked like this. So what does the slope mean? That 9.874 here. So basically what that means is for every unit increase in x, y is going to change by that much. So for our specific example, right, every pitcher I use, the game is going to run about 10 minutes longer. All right, what about the y-intercept? So that's telling us what happens when x is 0. So for our example, that was 99.397. All right, our slope is pretty useful, usually a pretty useful interpretation. Our y-intercept, though, doesn't always make a whole lot of sense. Right? And here in this example, it doesn't make a ton of sense because if we use 0 pitchers, there wouldn't be a game. Right? So it doesn't make sense to say a game's going to be 100 minutes with no pitchers. Right? It's really only meaningful when it could make sense for x to be 0, and it's really only useful when we actually have data for what happens when x is 0. Okay, so we know how to interpret that regression equation, a little bit how to calculate it. We don't want to worry about that too much. But what's another use for the regression equation? Well, one of its biggest uses is to predict for given values of x what's going to happen with y. Right? Again, remember our example. What if I said, well, I want to know what's going to happen if 8 pitchers are used? Right? We'll just plug 8 in there. So if I plug in 8, I get the game is going to be right around 3 hours. All right, so to wrap up, just a couple basic facts about regression. A couple things we want to think about. Well, what if I flip-flop x and y? Well, the correlation coefficient won't change. Your calculation of r, you were just multiplying stuff. Okay, so that won't change, but your regression line will change. Okay, so watch out for that. We mentioned that it's called our least squares line, and that least squares line does pass through x bar and y bar. All right, so thanks for watching. We'll see an example of this in the future and expand on these topics later. All right, thanks for tuning in, and we'll see you next time.